Hey, wonderful year 11s. So I've decided just to put this in a video just because I think it's faster for me to kind of do this the way that I want it done, and I think actually it's probably easier for you to listen than to read. So we're going to have a look at nuclear fusion, which is the process going on in stars. So the last thing I said was about stars and their life cycle. This is kind of a development on that, all about what stars are up to. So nuclear fusion is a process happening in stars all the time. It's the reason our sun looks the way it does. It's the reason we feel thermal or infrared energy coming from the sun. So we're going to have a look into that. First of all, I want you to attempt this worksheet. Okay, so pause the video, try the worksheet. Basically, this is about nuclear fission, which we've already carried out. We had a look at that, I think, at the end of year 10. So try and have a look at nuclear fission, all about nuclear fuel, etc., etc. So they will ask you all about in your exam. They will ask you all about the difference between fission and fusion, and this is very much in the A-level spec. So if people are looking, those of you who are looking into A-level, this is going to be majorly useful for you. You need to know the difference between fission and fusion. They're quite similar processes to an extent. So yeah, have a go at this worksheet. Please pause it, and I'll attach it anyway to show my homework. And then you guys can pause it here to self-assess as well, please. Okay, so what you guys need to be able to do, okay, is to explain what happens in a nuclear fusion reaction, to have a look at advantages and disadvantages of nuclear fusion, where we could use it in the world. Is it beneficial for us, or is it just useful kind of in space? And yeah, distinguish and be able to clearly explain the difference between fission and fusion. So fission, we've had a look at. Okay, we looked at that in our radiation topic. So fission is the splitting up of a large unstable nucleus by absorbing a slow moving neutron. Okay, so in those nuclear reactors, we're firing those very slow moving neutrons at these large unstable nuclei, and they are breaking those nuclei apart and releasing other neutrons at the same time, maybe a few other kind of tiny particles with them as well. Nuclear fusion is kind of like the opposite. So we have two light nuclei colliding at very high speeds. They have to be at super duper high speeds. Because if you think of just a nucleus, it has a positive charge. So if I'm trying to get two positive charges to come together, not only bump into each other, but to fuse and join, I'm going to need them to come in with a lot of energy. They are going to need enough energy to overcome the electrostatic repulsion caused by the fact that there are two positive charges there. Okay, so they must be coming together at super duper high speeds. They overcome that electrostatic repulsion, okay, and they fuse together. The way that they fuse together is A-level, but it's basically to do with this force. We call it the strong force that helps bind a nucleus together. Because if you think about a nucleus is full of protons, and protons are all positive. So how are they stuck in a little kind of sphere? Okay, and that's all to do with something called the strong force. Not needed at GCSE, but it's a nice way to kind of lead you into that A-level. Okay, so light nuclei, high speeds, fusing together, creating a larger, heavier nucleus. Okay, so yeah, hard enough that the nuclei fuse to become that heavier element, and we release a really large amount of energy when that happens. Okay, it's kind of like an explosion. Okay, they're coming together, they're overcoming all that electrostatic repulsion, and they're releasing a lot of energy when that takes place. Fission only works with heavy elements. Okay, nuclear fusion only works with lighter elements. Most of fusion is super duper light elements like hydrogen. Okay, helium maybe. In our sun, okay, so I talked about the fact that stars are doing this all the time. In the sun, we're probably looking at it's in its main sequence. Okay, so we're looking at probably only fusing hydrogen and helium really at the moment. Okay, we might be getting maybe up to some of the heavier elements, but not really. And our sun is quite a small star as well, so it will never really fuse very heavy elements. Okay, all the rest of the heavy elements that we know and have on the Earth, they were all either made in heavier stars, Okay, so they are fusing up to, well, yes, up to iron technically. And then the rest of the kind of massive elements are released and created during supernova explosion. So during that massive event of energy, which again we look at in more detail in an A level about how that really happens. Okay, so most commonly hydrogen. So having a look at some of these then. So we've got different isotopes of hydrogen. Hydrogen, which is our normal hydrogen, just one proton, one electron. Or we can have something called deuterium, proton, neutron, electron. Something called tritium, two neutrons, one proton, one electron. Notice how the proton number stays the same. Okay, there's always one yellow piece of Lego. And that is because if I change the proton number, this is no longer hydrogen. Okay, if I put another yellow piece of Lego in there, I've now got helium. Okay, so hydrogen only has one proton, so that the amount of yellow Legos must stay the same. I can add as many neutrons to that as I would like. Okay, it's going to get heavier. The element's not going to change. It's an isotope, isn't it? If I change the number of neutrons of a given element, I have an isotope. Okay, so these are the three different isotopes of hydrogen. Okay, so these are getting slightly heavier and heavier. So this doesn't change the way that the element reacts. It's still the same element. This is what an isotope is. Deuterium and tritium are 2 and 3 times as heavy as normal hydrogen. Okay, so isotopes, the exam style definition, which you need to know GCSE and A level, is isotopes are an atom of an element with the same amount of protons, same amount of electrons as normal, but a different amount of neutrons. Okay, and we look into isotopes a bit more a little bit later on. So nuclear fusion, what we've got, neutron and proton, okay, deuterium, add another proton, and we've ended up with helium-3. Okay, so proton and neutron coming together, that's given me deuterium, okay, a nucleus of deuterium. So normally in this state, while they're in stars, I have plasma, which means that there's such a massive amount of energy in there, the electrons are kind of stripped from their atoms. So tend to have nuclei, not atoms. Okay, so electrons not really involved in this at all. But as soon as I add one more proton, that is the process of fusion. Okay, these are two different atoms. One of them is just, if I've got one proton, I've just got, this is just normal hydrogen. One proton, one neutron, I've got deuterium. Okay, they have fused together. They've overcome that electrostatic repulsion. They have fused together and they've made helium-3. Okay, it's helium-3 because this is not quite normal helium. Okay, if I have normal helium, I've got another neutron in there, haven't I? Okay, so it's an isotope of helium. So inside stars, this is what's normally happening. We've got a proton, hydrogen, fusing with a neutron to make deuterium. Okay, so that's our first kind of process. Then that comes together and fuses again with another proton, and this makes helium-3. This is one of our kind of basic nuclear fusion reactions. This is one of the ones that would happen at the start, right at the beginning, where we've got plenty and plenty of protons and neutrons separated from their atoms, and they start to fuse. When that stops happening, we have to start fusing hydrogen with helium and things like that, and things get a bit more complicated. Okay, and then it can go on from there. So helium-3 fusing with another helium-3. I've ended up with helium-4, maybe a couple of protons. Those protons might go on to do something else. So all these reactions could be taking place, and it's just totally dependent on the amount of energy each of these atoms or nuclei has got. Okay, depends on what we're going to make next. So if I've got two helium-3 nuclei, we can make helium-4, which is obviously normal helium, isn't it? Lots of energy is released at every stage. Okay, and this is normally in the form of it's not light energy, is it? But we are releasing energy is being transferred in the form of light. Okay, it's actually technically kinetic energy, isn't it? Because we were seeing the movement. Yeah. So here's another example here. So we've got hydrogen forming to make helium, coming together with hydrogen, forming to make helium, coming together with another helium, and we've ended up with helium-4. Okay, so we started with two normal hydrogens, and we've ended up with one big helium at the end. Okay, so this is the process of fusion, things coming together to make something new at very high speeds, very high energies, enough to overcome electrostatic repulsion. So we can model these fusion reactions with simple equations, very similar to our kind of decay equations. Okay, so if we've got hydrogen 2 and hydrogen 1 coming together to make helium 3, we can put that in an equation. Okay, so hydrogen with a proton number of 1, mass number of 2, added to a hydrogen with a proton number of 1, mass number of 1, gives me a helium with proton number 2, mass number 3. And you'll notice if we make that arrow an equals, then if we look at the bottom numbers, the mass numbers, sorry, the proton numbers, 1 plus 1 equals 2. Look at the mass numbers, 2 plus 1 equals 3. Okay, so it's just like a normal mathematical equation. Those numbers need to add up. So a little bit of info then. Most of this is probably quite necessary for you to kind of have in notes. So nuclear fusion in stars is the only place that fusion is possible for a sustained period of time because of the massive amount of energy needed to do this. So at the centre of the star, we're looking at stupidly high temperatures and a very, very, very high gravitational force. Those two things coming together make those nuclei travel at stupidly high speeds and allow them to collide with massive amounts of energy. The combination of that high temperature, high pressure allows nuclear fusion to occur, and the heat released during that kind of explosion, during fusion, is what keeps the reaction going and going and going for kind of forever and ever and ever. So I'm going to put this video on as well because this is a really brilliant video. You need to know kind of the pros and cons of fusion and whether fusion would be a viable process for us to use as nuclear reactions on Earth. Okay, so we have nuclear reactions. They are nuclear fission reactions. We use fission in our nuclear power stations. Why are we not using fusion? So I will add this video in. You need to go and have a look at that. Write down the advantages, the disadvantages of using fusion instead of fission. Okay, that's kind of what that is. And then I'm going to add these exam questions. Yeah, I'm going to add those exam questions onto Show My Homework so you can have a look and try some exam questions on this. The key thing that you have to know about fusion, okay, you can't, you kind of low level question. Fusion occurs when two nuclei, okay, electrons not involved, two nuclei come together at massive speeds that overcome electrostatic repulsion. Okay, then you can go and talk about advantages, disadvantages. You can look at decay equations and go from there.